Assalamualaikum and good day. In today's lesson 6.5, we are going to learn how to find the Laplace transforms of three types of functions: Laplace transforms of piecewise continuous functions, periodic functions, as well as Dirac delta functions. So let's start with 6.5.1, the Laplace transform of a piecewise continuous function. Consider the piecewise continuous function f of t, which is defined as follows. F of t is equals to f1 of t larger than or equals to 0 less than t1, f2 of t larger than or equals to t1 less than t2, and there may be several more other functions within several more other subintervals, and f of t is equals to f sub n of t for t larger than or equals to t sub n. Okay, so this function f of t is said to be piecewise continuous because within the interval 0 until infinity, the interval is subdivided into a finite number of subintervals on which there is a continuous function in each subinterval. Besides, there is a finite limit at the endpoint of each subinterval. Okay, so this function f of t is a piecewise continuous function. Now let us learn how to write f of t in a single form, or in other words, in compact form. We are going to learn how to write f of t in a single line, and how is it going to be done? We are going to use the unit step function. Okay, so in terms of the unit step function, the function f of t can be expressed in a single form, and the formula is as follows. Okay, so f of t is equals to, now we start with the first function within the first subinterval, and notice that the endpoints of the first subinterval is 0 and t1. So we write down f1 of t multiplied by ut minus 0 minus ut minus t sub 1 plus, for the second function it is f2 of t, and the end limits for the second interval is t1 and t2. So we write f2 of t multiplied by u t minus t sub 1 minus u t minus t sub 2. And for the last subinterval, we write down f sub n of t multiplied by u t minus t sub n. Okay, this is the subinterval t larger than or equals to t sub n. So notice that this function f of t from piecewise continuous cannot be written in a single form, in a single line, by using the unit step function. Example, express the piecewise continuous function f of t in terms of the unit step function and then find its Laplace transform. F of t is equals to 1 for t larger than or equals to 0 less than 1. F of t is equals to t for t larger than or equals to 1 less than 2. F of t is equals to 3 for t larger than or equals to 2. Okay, so this function f of t is a piecewise continuous function, and we are going to write this piecewise continuous function in single form by using the unit step function. Okay, so f of t is equals to, now start by writing down the first given function. In this question, the first given function is the number 1, so you write down number 1 here, multiplied by, now consider the endpoints of these subintervals. The left endpoint is the number 0 and the right endpoint is the number 1. So for this number 0, we write down the unit step function in the form of ut minus 0. And for the right endpoint, the number 1, we write down the unit step function in the form of ut minus 1. So we write down ut minus 0 minus ut minus 1. Okay, so take note, the unit step function that relates to the left endpoint subtract the unit step function that relates to the right endpoint. So it shouldn't be the other way around. Do not write ut minus 1 minus ut minus 0. Okay, it should be ut minus 0 minus ut minus 1. Plus, now the next function is t. So we write down plus t. If it is written here as negative t, so you write negative t here. Okay, but in this case, it is positive t. So plus t multiplied by, now for the second subinterval, the left endpoint is the number 1. So corresponding to this number 1, we write down the unit step function in the form of ut minus 1. And the right endpoint is the number 2, so the unit step function will be written as ut minus 2. So we write down t multiplied by ut minus 1 minus ut minus 2. And for the last function, in the last subinterval, it is the number 3, so we write down plus 3 multiplied by ut minus 2. Okay, so this function f of t from piecewise form has now been expressed in a single form by using the unit step function. Okay, now our next task is to find its Laplace transform, but before we can do that, we need to simplify this expression first. Now we know that ut minus 0 by definition is equals to 1. Alright, so now let us expand this expression, open up the bracket. So f of t is equals to 1 multiplied by 1 minus 1 multiplied by ut minus 1 plus t multiplied by ut minus 1 minus t multiplied by ut minus 2 plus 3 multiplied by ut minus 2. Okay, so this is how we have written down the function after we have expanded this whole expression here. And notice that these two terms have common unit step function, which is ut minus 1, and for the last two terms they also have common unit step functions, which is ut minus 2. So let us factor the common unit step function. Okay, so it equals to 1. Now between these two, we are going to factor ut minus 1, and within this bracket, let us write down the coefficient of each of these unit step function. Okay, so I write down the coefficient for this unit step function, which is positive t, and the coefficient of this unit step function is negative 1, so negative 1. So t minus 1, ut minus 1. And for the last two terms here, the common unit step function is ut minus 2, so we factor ut minus 2, and inside the bracket we write down the coefficient of these unit step functions. Okay, so minus, and then I put a t here, because this t is the coefficient of this unit step function, and plus 3. Now since we have already written down negative sign out here, so we should put a negative sign inside here, because negative is positive. Okay, so positive 3, so we will write down negative t minus 3 ut minus 2. Now notice the way we write down this function. Okay, it is preferable that we put a negative sign inside this bracket here. Okay, so alright, so that it can match with the formula given in the Laplace transform table, formula number 21. Okay, so let us find the Laplace transform of f of t, which is the Laplace transform of 1 plus the Laplace transform of t minus 1 ut minus 1 minus the Laplace transform of t minus 3 ut minus 2. Okay, now how do you find the Laplace transform of 1? That's very easy. From the table of Laplace transform, we can get it directly from rule number 1. But what about this? And what about this? Okay, which formula from the table of Laplace transform are we going to use? In the table of Laplace transform, there are three formulas which involve the unit step function. Formula number 21, Laplace transform of f of t minus a ut minus a. Formula number 22, Laplace transform of ut minus a. Formula number 23, Laplace transform of gt ut minus a. Okay, so all these formulas involve the unit step function ut minus a. Now this is the main formula. Formula 21 is the main one. 22, 23, as I have discussed in the previous slides, they are derived from formula number 21. Okay, now look at this problem here. Laplace transform of t minus 1 ut minus 1. Notice that the function u is expressed in terms of t minus 1, and this function is also expressed in terms of t minus 1. If they are of the same form, then we have to apply formula number 21. Okay, because if this is in ut minus a, and the function f is also expressed in terms of t minus a, then we have to apply formula number 21. Okay, so formula number 21, where a in this case is equals to 1. What about this one here? Do we use formula number 21? Okay, now this is in terms of t minus 2, but this is not in terms of t minus 2, and therefore it is advisable to use formula number 23 instead. Okay, we use formula number 23 because if this is in terms of t minus a and the function g is a form not similar to the form given in the unit step function, then we better use formula number 23. So in this case, a is equal to 2. Right, now Laplace transform of 1 is 1 over s plus, now for the second part here, we're going to use formula number 21, which is e to the minus as. Now a is equals to 1, so we e to the minus 1s. Laplace transform of f of t. Now if Laplace transform of f of t minus a is t minus 1, therefore Laplace transform of f of t must be just t. Okay, so e to the negative s, Laplace transform of t. Okay, so t minus 1 is the function of t translated 1 unit to the right. Minus, okay, the next one I'm going to use formula number 23, e to the minus 2s, where a is equal to 2. Laplace transform of, for the function g, the t must be replaced by t plus a. So this is the original function. Now this t must be changed into t plus a, where a is equal to 2, so we write down t plus 2 minus 3. Okay, so this one is replaced by t plus 2 minus 3. Is equals to 1 over s plus e to the minus s, the transform of t we know is 1 over s squared, minus e to the minus 2s. Now let us simplify the expression inside this bracket. Laplace transform of t plus 2 minus 3 becomes t minus 1. And the last step is to get the Laplace transform of this. And so the final answer will be the Laplace transform of f of t is equals to 1 over s plus e to the minus s times 1 over s squared minus e to the minus 2s. Laplace transform of t is 1 over s squared minus Laplace transform of 1 is 1 over s. Okay, so this is the first Laplace transform for the given piecewise function f of t. 6.5.2 Periodic function. A periodic function is a function that repeats its values in regular intervals or periods, and the graph of a periodic function is obtained by periodic repetition of its graph on any interval. Let us look at the graph of a sine function defined from 0 until infinity. Okay, so notice that the graph makes one complete cycle from interval 0 until 2 pi, and the graph repeats itself after every 2 pi units. Okay, so it seems that the period t is equals to 2 pi, alright, and we say sine t plus 2 pi is equals to sine t. It means that the graph of sine t keeps on repeating itself after every 2 pi units. So in general, for every periodic function, we write f of t plus the period is equals to f of t for all t larger than or equals to 0. Let f of t be a periodic function with period t, and that f of t is piecewise continuous on 0 infinity. Okay, so f of t is periodic and the period is given by capital T. The Laplace transform of the periodic function f of t has this formula. Laplace transform of f of t is equals to 1 over 1 minus e to the power of negative s times capital T, which is the period, multiplied by the Laplace transform of h of t. Now what is h of t? H of t is the function f of t specified over one period only and 0 elsewhere. So that is, h of t is equals to the function f itself for t larger than or equals to 0 less than capital T. In other words, h of t is the function f of t in the first cycle, and h of t is equals to 0 for t larger than or equals to capital T. In other words, h of t has been suppressed to 0 after the first cycle. Okay, notice that this h of t is given in piecewise form. So to determine the Laplace transform of h, okay, we need to firstly rewrite the function h in a single expression by using the unit step function. Okay, so take note, this is the formula for the Laplace transform of the periodic function, and this formula of Laplace transform for the periodic function is not given in the table of Laplace transform. Example, find the Laplace transform of the periodic function whose graph is given by the following figure. Okay, so this is the function f of t defined from 0 until infinity, and we are interested to find the Laplace transform of this function. Now this function is said to be periodic, so let us determine the period capital T. Notice that the function f of t is equal to 3 from 0 until pi, and it is equal to negative 3 from pi until 2 pi. So this is the complete cycle for the function f of t, and it keeps on repeating the same pattern over and over again for every 2 pi units. So we say that the period capital T is equal to 2 pi. Now let us write down the function f of t for the first cycle. Okay, so f of t is equals to 3 for t larger than or equals to 0 less than pi. Okay, so this is the first subinterval, and it is equals to negative 3 for t larger than or equals to pi less than 2 pi. So this is the second subinterval for the function f of t within the first cycle. Okay, so this is the description of the function f of t in the first cycle, and we want to indicate that the function f of t is repeating itself after every 2 pi units. So we need to write down the following statement. We say that f of t plus 2 pi is equal to f of t for t larger than or equals to 2 pi. Okay, so the function f of t repeats itself after every 2 pi units, starting from the point t equals to 2 pi. Now in the previous slide, we mentioned the function h. Now what is the function h? The function h is similar to the function f only in the first cycle. But after the first cycle has been completed, the function f has been suppressed to 0. Okay, so we write down h as follows. H of t is equal to 3, okay, for t larger than or equal to 0 less than pi, and it is equal to negative 3 for t larger than or equals to pi less than 2 pi, and it is equal to 0 for t larger than or equals to 2 pi. Okay, so this is the function h of t, and it is given in piecewise form. So we are going to write h of t in single form, because after this we are required to determine the Laplace transform of h of t. So to rewrite h in single form, we are going to use the unit step function. Let us refer to the function h of t once again. So this is the function h of t. It is a piecewise continuous function defined from t larger than or equal to 0 until infinity. And we are interested to find the Laplace transform of h of t. Now before we can get to that, let us rewrite h of t in a single form by using the unit step function. So we write as follows. H of t is equals to, now the first function given within the first subinterval is the number 3, so you write 3. And for the first subinterval, the two endpoints are 0 and pi, so we write down ut minus 0 minus ut minus pi. The next function is negative 3, so we write negative 3 multiplied by, okay, for the second subinterval, the endpoints are pi and 2 pi, so we write negative 3 multiplied by ut minus pi minus ut minus 2 pi. And for the last function, in this last subinterval, it is just equal to 0. So we write down 0 multiplied by ut minus 2 pi. Now 0 times anything is equal to 0. So this part here, you don't have to write it at all actually. Now we know that ut minus 0 equals to 1. So now let us expand this and by opening up the bracket. So h of t is equals to 3 times 1, which is 3, minus 3 times ut minus pi, minus 3 times ut minus pi, plus 3 times ut minus 2 pi. And notice that these two terms have common functions, common unit step function, which is ut minus pi, So combining those two, we get 3 minus 6 ut minus pi plus 3 ut minus 2 pi. Okay, so this is the function h written in single form by using the unit step function. And now we're going to find the Laplace transform of the function h. That means we need to find the Laplace transform of 3 minus 6 times the Laplace transform for this unit step function ut minus pi plus 3 times the Laplace transform of ut minus 2 pi. Alright, and what is the Laplace transform of ut minus pi, and what's the Laplace transform of ut minus 2 pi? So certainly we need to refer to formula number 22, where the Laplace transform of ut minus a is equals to e to the negative as over s. So for this part here, if we use formula number 22, we identify a as equals to pi, and for this part of the problem, a is equals to 2 pi. Also refer to formula number 22. So Laplace transform of h is equals to Laplace transform of 3 is very simple. This is just 2 over s minus 6 multiplied by, now using formula number 22, replace a by pi. So the answer will be e to the negative pi s over s plus 3 times Laplace transform of ut minus 2 pi. Again, refer to formula number 22, where a now is 2 pi, so be e to the power of negative 2 pi s over s. Okay, so this is the Laplace transform of h, and if you are interested, you can rewrite this. You can bring 6 up here and 3 up here. Now the Laplace transform of the periodic function is given by this formula, 1 over 1 minus e to the minus s capital T multiplied by the Laplace transform of h. Okay, so what I'm going to do now is to substitute capital T by 2 pi, because period is equal to 2 pi, and Laplace transform of h is this whole expression that we have just derived. Okay, so we say the Laplace transform of f of t is equals to 1 over 1 minus e to the minus 2 pi s, and this is the Laplace transform of h, which is 3 over s minus 6 times e to the minus pi s over s plus 3 times e to the minus 2 pi s over s. In this next example, we are asked to find the Laplace transform of the function f of t, where f of t is equals to 2t for t larger than or equals to 0 less than 2, f of t is equals to 4 for t larger than or equals to 2 less than 4, and f of t plus 4 is equals to f of t for all t larger than or equals to 4. Even though the graph of the function f of t is not provided in this problem, but we know that we are actually dealing with a periodic function because of this statement. This statement indicates that this function f of t is repeating itself after every 4 units. And this is the description of the function f of t in the first cycle. Okay, so let us determine the function h of t. Okay, so h of t is equals to, as we know, h of t is similar to the function f in the first cycle. Okay, so this is the function f in its first cycle, and once the function f has completed its first cycle, the remaining part of the graph has been turned off to 0. Okay, so h of t is equal to 0 for t larger than or equals to 4. And based on our observation, we know that the period is equals to 4 units. So, since h of t is a piecewise continuous function, we can rewrite it in a single form by using the unit step function. So, h of t is equals to, okay, the first function given in the first subinterval is equal to 2t, and the endpoints for the first subintervals are 0 and 2, so we write ut minus 0 minus ut minus 2. Okay, so 2t multiplied by ut minus 0 minus ut minus 2 plus the second function is given by the constant 4 multiplied by ut minus 2 minus ut minus 4. Okay, the endpoints for these subintervals are 2 and 4. And lastly, the last function in the last subinterval is 0, so 0 multiplied by ut minus 4. Now, since 0 times anything is 0, we can actually disregard this term. Now we know that ut minus 0 is equals to 1, so h of t is equals to 2t multiplied by 1 minus 2t multiplied by ut minus 2 plus 4 multiplied by ut minus 2 minus 4 multiplied by ut minus 4. Notice that for these two terms, the common unit step function is ut minus 2, and these two terms also have common number 2. So we write as follows, 2t minus, okay, so factor the number 2 from these two terms, minus 2, and factor the unit step function ut minus 2. So inside this bracket, we write down, okay, now since for the first term, 2 has been taken out, and ut minus 2 has been taken out, so what remains is t. And for the second term, ut minus 2 has been taken out, and 4 is 2 times 2, so 2 has been taken out, so inside here we should put negative 2. Now take note, we put negative 2, not positive 2, because negative 2 times negative 2 gives positive 4. So whatever we write here, we must ensure that we get back the same as the original given expression as in this line here. Alright, so this is the function h of t that we have simplified, and now we're going to determine its Laplace transform. So we write down the Laplace transform of h of t is equals to 2 times the Laplace transform of t, okay, minus 2 times the Laplace transform of t minus 2 ut minus 2, minus 4 times the Laplace transform of ut minus 4. Alright, so we need to find the Laplace transform that involves unit step functions for this term here and also for this term. So let us recall the formula that we can apply to find the Laplace transform of each of these functions. So we can use formula number 21 for this part here, okay, where a is equal to 2. Notice that we use formula number 21 because the unit step function is expressed in terms of t minus 2, and this function here is also expressed in terms of t minus 2. So they have the similar form, and therefore we are going to apply formula number 21. Now remember, if these two are not the same form, then we apply formula number 23. Whereas for this part here, we apply formula number 22, transform of ut minus a, where a is equals to 4. Okay, let us continue. Transform of t is 1 over s squared, so 2 times transform of t becomes 2 over s squared minus 2 times. Now applying formula number 21, the formula is e to the minus as. Now a is equal to 2, so e to the power of negative 2s times the Laplace transform of f of t. Now if f of t minus a is t minus 2, therefore f of t must be simply t. Alright, so we write 2e to the minus 2s times Laplace transform of t minus 4 times Laplace transform of ut minus 4 based on formula number 22, where we now replace a by the number 4. So we write minus 4 times e to the negative 4s over s. So Laplace transform of h of t is equal to 2 over s squared minus, now Laplace transform of t is 1 over s squared, so this term becomes 2e to the negative 2s divided by s squared minus 4e to the negative 4s over s. Okay, so this is the Laplace transform of h of t, and now we are going to determine the Laplace transform of f of t based on this formula. So Laplace transform of f of t is equals to 1 over 1 minus e to the negative 4s. Okay, we have replaced capital T by 4, because the period is equals to 4. And Laplace transform of h, we got it from what we have worked out just now, which is 2 over s squared minus 2e to the minus 2s over s squared minus 4e to the negative 4s over s. Okay, so this is the answer for the given problem. We have obtained the Laplace transform of the given periodic function, which is described as this one here. We have now reached the final subsection of 6.5, 6.5.3, the Dirac delta function. The Dirac delta function is named after an English physicist, Paul Dirac. Paul Dirac made significant contribution to physics in the 20th century. The Dirac delta function is a forcing function that exerts a large force over a very short interval of time. So here we are talking about a function or a force which is very, very large, and this very, very large force acts over a very short duration of time. For example, let's say we strike a nail with a hammer. So the striking of the nail is considered as a large force because we are exerting a large force onto the nail, and the striking of the nail takes over a very short period of time. It may take a split of a second to strike the nail with the hammer. Okay, so here we're talking about a forcing function that acts over a very short interval of time. A hammer striking a nail. Another example of a forcing function is when a tennis racket hitting a ball. The Dirac delta function is a function that is zero everywhere except at one point t equals to t0. At this point, the Dirac delta function has an infinite value. So let's look at this graph. Okay, this graph describes the Dirac delta function, and suppose t0 is the time along the t-axis. So we say t equals to t0. So the Dirac delta function at the point t equals to t0 has an infinite value. Okay, so the graph is very tall. It is infinitely tall and it is infinitesimally narrow. Alright, but for the points other than t0, the function is equals to 0. Alright, so this is the forcing function, a very large force that acts over a very short interval of time. The formula for the Laplace transform of the Dirac delta function can be found in this table of Laplace transform at row number 26. Okay, so the Laplace transform of delta t minus t0 is equals to e to the power of negative s t0. So this expression delta t minus t0 represents the Dirac delta function where a large force is acting about the point t equals to t0. What is the Laplace transform of delta t minus 2? Okay, so delta t minus 2 represents a forcing function that acts about the point t equals to 2. So to get the Laplace transform, you simply have to replace t0 by 2 in formula number 26. So Laplace transform of delta t minus 2 is equals to e to the power of negative s multiplied by 2, which is the same as e to the power of negative 2s. What is the Laplace transform of delta t minus pi? So here we are talking about a forcing function, a very large force that acts about the point t equals to pi. So to get the Laplace transform of delta t minus pi, we use formula number 26 again, but this time t0 is equals to pi. So the answer is e to the power of negative pi s. What is the Laplace transform of delta t? So delta t is the same as delta t minus 0. So here we are talking about a forcing function, a huge force that acts about the point t equals to 0. So the Laplace transform of delta t can be found by using formula number 26, where the t0 is replaced by 0. So we get e to the power of negative s multiplied by 0, which is just equals to 1. So we conclude that the Laplace transform of delta t is simply equals to 1. In this problem, we are going to use the method of Laplace transform to solve the following initial value problem. Y double prime plus 4y prime plus 3y is equal to delta t plus delta t minus 4, y0 is equal to 0, y prime of 0 is equal to 2. Okay, so this is the second order, non-homogeneous, linear DE with constant coefficients, and these are the two initial conditions. And notice that this equation cannot be solved using the method of superposition and also the method of variation of parameters, because those two methods cannot be applied to solve equations involving functions which have infinite values such as the Dirac delta function. Okay, so this is the advantage of learning Laplace transform. Laplace transform can be used to solve equations involving the Dirac delta functions. So firstly, we are going to find the Laplace transform of each term on each side of the equation. So take the Laplace transform of y double prime, transform of y prime, and transform of y. Okay, and on the right side, we take the Laplace transform of delta t and also the Laplace transform of delta t minus 4. What is the Laplace transform of y double prime and what is the Laplace transform of y prime? We have already learned how to obtain these formulas in section 6.3. So if you have forgotten, please refer to 6.3 once again. Okay, so the Laplace transform of y double prime is given by s squared ys minus sy0 minus y prime of 0. plus 4 times the Laplace transform of y prime. Okay, formula for Laplace transform of y prime is sys minus y0 plus 3 times, now Laplace transform of y is simply ys. On the right side, the Laplace transform of delta t and Laplace transform of delta t minus 4, we can get these results by referring to formula number 26 in the table of Laplace transform. Okay, so Laplace transform of delta t is equals to 1 and Laplace transform of delta t minus 4 is e to the power of negative 4s. At this step, we can incorporate the initial conditions. Okay, y0 is equal to 0. Okay, so this term will be equal to 0. Similarly here for this term, it will be equal to 0 and y prime of 0 is equal to 2. So afterwards, we are going to replace this term by negative 2. Okay, so we have s squared ys minus 2 plus 4s ys plus 3 ys is equals to 1 plus e to the power of negative 4s. Okay, now on the left side of the equation, there is a constant 2 which is not multiplied by ys, so we are going to transfer this negative 2 to the other side. Whereas for the remaining terms, they all have common function ys, so we are going to factor the ys. Alright, so we write like this: s squared plus 4s plus 3 multiplied by ys. Okay, this s squared and 4s and 3, they are the coefficients of the ys on the left side of the equation, and on the right side we have shifted negative 2 to the right, so 2 plus 1 gives 3. So on the right side the expression is 3 plus e to the power of negative 4s. Divide the whole equation by this quadratic factor, so you get ys is 3 divided by s squared plus 4s plus 3 plus e to the negative 4s divided by s squared plus 4s plus 3. Now we want to find y of t, which is the solution for this equation, and to get y in terms of t, we are required to determine or to find the inverse of ys. Okay, so we write yt is the inverse of the first term plus the inverse of the second term. But notice that the denominator of these two terms is a quadratic factor. Okay, they are the same. And this quadratic factor can be factorized. Okay, s squared plus 4s plus 3 can be written as s plus 1 multiplied by s plus 3. Okay, so for the first term, it becomes 3 over s plus 1 times s plus 3, and for the second term, e to the negative 4s divided by s plus 1 times s plus 3. Okay, so by the linearity of the inverse transform, we can actually split this into two problems of inverse transforms. So we write y of t is the inverse of the first term, 3 over s plus 1 times s plus 3 plus inverse of the second term. Now the second term involves e to the power of negative 4s, and therefore we know that we need to refer to formula number 21 in order to get its inverse function. Okay, so we start by taking out e to the negative 4s using formula number 21, and therefore the fs must be this expression here, which is 1 over s plus 1 times s plus 3. Okay, now assuming that you already know how to apply partial fraction, so the partial fraction decomposition for 3 over s plus 1 times s plus 3 is given by the following. It is 3 over 2 times s plus 1 minus 3 over 2 times s plus 3. Okay, so this is the partial fraction decomposition for the function in the first term, plus the inverse of e to the negative 4s, and the partial fraction decomposition for this function is given by 1 over 2 times s plus 1 minus 1 over 2 times s plus 3. Alright? Now, the inverse for the first function is 3 over 2 multiplied by e to the power of negative t. Now, how do we get e to the power of negative t? Because the inverse of 1 over s plus 1, using formula number 4 in the table of Laplace transform, is e to the power of negative t. Minus 3 over 2, okay, and the inverse of 1 over s plus 3 is e to the power of negative 3t. So this is the inverse for the first function, or the first term, plus, okay, the inverse of the second term. Alright, now we have the constant half, and the inverse of 1 over s plus 1 is given by e to the power of negative t. But since this function is multiplied by e to the negative 4s, According to the rule, when we apply formula number 21, the t must be replaced by t minus a, where a in this case is 4. Okay, so the inverse of 1 over 2s plus 1, instead of half e to the negative t, it becomes half e to the negative t minus 4. And for the second part, minus half, the inverse of s plus 3, inverse of 1 over s plus 3 is e to the power of negative 3 t, and that t need to be replaced by t minus 4 because this function is multiplied by e to the negative 4s, and this is not complete unless you multiply all of this by ut minus 4. Okay, so if you have forgotten how to get all this, please refer to section 6.4. Okay, we have discussed in detail how to apply formula number 21 in order to get this result. Okay, so therefore we write down the function y of t as a solution for this IVP is given by 3 over 2 e to the power of negative t minus 3 over 2 e to the power of negative 3t plus half e to the power of negative t minus 4 minus half e to the power of negative 3 t minus 4, and all of this is multiplied by the unit step function ut minus 4. So as a summary, let us recall what we have learned today. We have learned how to find the Laplace transform of a piecewise continuous function, the Laplace transform of a periodic function, and the Laplace transform of a Dirac delta function. So it seems that the Laplace transform has its advantages. It can be used to solve problems involving these types of functions, whereas the methods such as the superposition and also the variational parameters cannot be applied to solve problems involving these types of functions.